Welcome back, everyone. Professor Cameron here. Now, in our last video, we went ahead and we modeled this piece here, this bracket. Now, today what we're going to do is we're going to go ahead and create our engineering drawing for this piece. And then we're going to work on how our engineering drawing and how our model are actually linked together. Now, the purpose of our engineering drawing is so that we can have this part manufactured. In engineering, very rarely do we want to send 3D models to our machine shop. So what we do instead is we send a document. It contains a layout of our model, and it contains all the necessary dimensions, notes, and that information. So that's what we're going to do here. So once we have this part open, what we're going to do is we're going to go to File, and then Make Drawing from Part. And when we select that, what it's going to do is it's going to open up a window that looks like this here. And what it's asking us to do is to select a paper size. Now in ANSI is the format that we create our engineering drawings in. I'll talk a little bit more about this in a second. We have a few different sizes of paper, A through E. Now, the only difference between these is the size of the paper. A is just standard 8.5 by 11 inch printer paper. B is twice that size, it's 11 by 17. C is twice that size, 22 by 17. And I'm sure you guys have guessed D and E follow the same pattern. They get exponentially larger. There's no hard and fast rule as to what paper size you choose. Typically, the simpler your part, like cubes, spheres, basic rectangles, those can fit easily on an A. B is good for sort of medium complexity parts. C is good for, larger parts, complex parts, assemblies. And then D and E are both large format prints. Those are good for parts that need to be printed out 1:1 scale, really detailed drawings, large assembly prints, stuff like that. You sort of use your best judgment. Most drawings are going to be on A, B, or C paper. Today, what we're going to do is we're going to choose the option B, Landscape. Now, if you don't see this option, there's a checkbox here, only shows standard formats. Either check or uncheck that box until you can see the B ANSI landscape option. So once we've got that, we can go ahead and apply changes or click OK. And that's going to give us our 11 by 17 inch piece of paper. Now, before we can start modeling here, what we want to do is go ahead and set our units. Now, since we modeled this part in inches, we want to create our drawing in inches. Very rarely do you want to model in one set of units and create your drawing in another. There's rounding issues and it's not quite clean. So what we're going to do is we're going to model this in inches. Next, what we have to do is tell Solidworks what drafting standard we want to create this drawing in. For that, we're going to come up here to our options. We're then going to select Document Properties. And under Overall Drafting Standard, we want to select ANSI. ANSI is the American National Standard. The other standard that you're likely to see is ISO. ISO is the international standard. Other countries also have their own. Germany, Japan, Britain, China, the mining industry. Right? The meat and potatoes between all of these are exactly the same. It's an image that you're putting dimensions on. The only thing that changes is how our images are displayed, how our dimensions are interpreted, stuff like that. So what we're going to do is we're going to select ANSI. And OK. So now we've got everything all set, so we can go ahead and start to put our views onto this drawing. We can start to put our images on. on our right hand side we have this view palette. And this will give us all of our views for our model. Now what we're going to do is we're going to go ahead and put on our standard 3 orthographic views. We're going to click our front view and then just drag it on. Click and hold down and drag it on. We can place it somewhere over here. Now when we drag our cursor around, do you see how it's letting us place subsequent views? What we're going to do is we're going to place our right side view, and then we're going to place our top view. And then if you drag this out at a bit of a 45-degree angle, right like that, it will let you place what's called an isometric view. We're going to go ahead and put that down as well. Now the ISO view, this is good for just giving us a representation of what our part looks like. Sometimes based on the ortho views it can be a little tricky. So the ISO view is good for that. We don't actually dimension this view. This is just for reference only. It's these ortho views that we're going to dimension. Now, the next thing we're going to do is take these views and blow them up. We're going to make these views much larger. We have a lot of free space on this drawing, and we don't want to waste that, right? So what we're going to do is we're going to come down here next to our scale, and we're going to select 1:1, right like that. Now this looks a little overcrowded right now, but that's fine. We're gonna alter this so that it looks good. So 1:1 scale. Now, you noticed our ISO view also blew up at the same time. That's because all these views are linked together. Our ISO view, since it's just for reference, we don't need it to be that big. So what we can do is we can come in here and we can right-click on this view. We can select from scale over here. It has 3 options. Use parent scale, sheet scale, or custom scale. Parent scale is taking the scale that we applied to this parent view. This first view that we put on as the parent. Sheet scale is using the scale we applied to the sheet. That's this scale over here. We're going to select the third option, use custom scale. And we are going to set this back to 1/2. Right like that. Now when we look at our ortho views here, one thing we don't want is to have views that don't serve a purpose. Our standard format is our front view, top view, and right side view. However, we aren't bound to that. We could have just one view, we could have 2 views, standard 3 views. We could add more views. We could have a full set of 6 or so views. So if a view isn't serving a purpose for us, we delete it. Now specifically this right side view. This view isn't giving us any new information that our front and top views aren't giving us. All it's giving us is the height of this part, which we get from our front view. It's giving us the width or the thickness of this part, which we get from our top view. And it's giving us the thickness of this tab, which we also get from that top view. So what we can do is we can actually delete this, and that's exactly what we're going to do. We're just going to right click and delete. Yes. And there we go. That frees up a little bit more room on our drawing, and we should be good. So what we can do now is we can go ahead and start to dimension this. So what we're going to do is we're going to focus on this top view here. What we're going to start off with first is dimensioning the location of these holes. So we're going to come in here with Smart Dimension, and we're going to dimension the distance from this first hole to this second hole. Right like that. Next, what we're going to do is we're going to dimension the distance from this first hole to this center hole. We're then going to dimension the diameter of this smaller hole and the diameter of this hole here on the side. So that all looks pretty good. What we're going to do now is dimension the radius of this outer arc. And then all we have left to do on here is to dimension the overall thickness of this centerpiece. So we're going to dimension from here to here and drag that off to the side. And that all looks good. Now, on our view here, you may have noticed these center crosses. These obviously denote the center point of a circle, but they also serve another important role. If you'll notice, you see how the center cross has these extensions on it. What we're going to do is we're going to take the little nodes and just extend them out so that they just barely extend off of our part. This one here, this is actually going to meet up with the center one. And I'll explain the purpose of these, why we're doing this specifically. Right like that. Now, we can define our model using dimensions. We can also define it using the center marks and what we call applied geometry, or implied geometry. Right? If we have this center mark that runs all the way straight through these circles, we can imply that these circles are all on the same height, right? These are all in a line. So that way we don't have to come in here and dimension the heights for each of these circles. These arcs share the same center points as the circles. So we can assume that the circles are in line with the center point of this arc. And we have a line that runs through the entire part this way, and a line that runs through our entire part this way. So what that allows us to infer is that our part is symmetric, top and bottom, and left and right. So what that does is it just alleviates the amount of dimensions we have to put on here. So this looks good. What we can do now is we can focus on this view here. We're going to grab Smart Dimension, and we're just going to dimension the thickness of this tab here. Right like that. We are going to dimension the outside radius, right here. And then we're going to dimension the inside radius. Right like that. Now, we have some holes running through this. So what we want to do is we want to make those holes visible on this view here. To do that, what we're going to do is we're going to click on this view, and then on our left hand side we're going to select Hidden Lines Visible, right like that. That way we can see the holes running through here. Now, do you notice this solid black line here that's running through the center of that hole? That line is what we call a tangent edge. And that forms whenever we have an arc that tangentially mates to a straight segment. Right? It's this node right here. Solidworks interprets those as straight lines. What we're going to do is we're going to remove those tangent edges. To do that, we're going to right click on our view here, select tangent edges, and then tangent edges removed. And that looks pretty good. Now, so we can imply that these are holes, what we're going to do is we're going to put in a center line. Under our Annotations tab, we have a center line tool. What it's asking us to do is to manually insert a center line, select the two segments that create this line. So what we're going to do is we're just going to come over here and select the two bits that make up that hole, like that. We're going to do that on the top as well, and on the right. That looks good. The next thing we're going to do is to put in a center mark for this hole. Right now we have this dimension here, and it's not really dimensioning to anything, right? It's coming to this point right here, and that's really not good practice. So what we're going to do is we're going to grab our center mark, and then all we have to do is just click the arc we want that center line to go to. Right like that. What we're going to do is right here, do you see how these aren't quite clean? They extend over just a little bit, and it won't actually let you shrink these extension lines. So what we're going to do is, for this center mark, we're going to select Use Document Defaults. We're going to uncheck that. And then we're going to turn off extended lines, so that we just have this tiny little cross here. Now we do want those, so what we're actually going to do is draw them back in. We're going to go to our Sketch tab, select our Line tool, and come in here, and we're going to leave a little bit of a gap. And we're just going to draw in that extended line, and leave a little bit of a gap on the other side. And then we're going to do the same thing, but this time we're going to connect it going straight up. We're going to connect it to this center line. Right, like that. That looks pretty good. Now at this point, right, this here, specifically this dimension, this is a clamp, right? This is going to clamp onto a round object with a diameter of 2.5. The way we have this dimensioned is technically correct. However, one thing we might want to do is to display this internal arc here as a diameter instead of a radius, because this is going to clamp to a 2.5-inch diameter pipe, and we dimension pipe on the diameter. So what we're going to do is we're going to click on this dimension here. We are going to go to liters on our left-hand side. And then right here, we are going to select diameter. That looks pretty good. Now this looks a little strange to us. So what we're going to select is inside. And then there we go. So that looks fine. So what we can select now is OK. Now, one thing we want to remember is that our models are linked directly to our drawings. So any change that we make in our model will update in our drawing. So let's go ahead and do that. If we go back to our model, let's take a look at the base here. Let's edit that sketch. Now, this hole here has a diameter of a 1/2 inch. Let's make that 0.625. You can see it rounds it to 0.63. That's actually 0.625. We'll actually address this issue in our drawing. We can click OK. And those holes are now slightly larger. Same with this circular extrude. Let's go ahead and edit that as well. And instead of a radius of 1.75, let's make this a radius of 1.625. And that looks good. So it's just slightly smaller. So we've altered a couple dimensions. Now let's go back to our drawing. You can see it's updating for us. And if we look at this radius and at this diameter, they've updated to those new diameters. Your drawings and your models are linked. So anytime you make a change to a model, it will update in the drawing and in the assembly for you. Now, like I said, this is actually 0.625 for both of these. However, it's rounding it to 0.63. What we want to do is we want to click on that dimension. And under tolerance and precision, we're going to set it to a 3 decimal place value so that it's showing 0.625. We're going to do that for both of these. That looks good. When we turned on hidden lines for our ISO view also turned on. That kind of clutters up this view here. So what we're going to do is we're just going to click on that and make that hidden lines removed. And that looks fine. So this all looks good. Now what we've done is we've gone ahead and we've put in all of the, or most of the technical information. What we got to do now is come down here and fill out this block of information right here. This is called our title block, and this contains administrative information like who made this part, where it came from, and then some minor technical information. So what we're going to do is we're going to right-click somewhere on our drawing and then select Edit Sheet Format. Our drawing will disappear, and that's fine, but now we can edit this block of information. So what we're going to do is we're going to come in here, and in this first block, if you mouse over towards the center of this block, you'll see a little A pop up next to your cursor. When you see that, you can double click and you can edit this text box. And this box is for your company name or your institution name. And we can go ahead and put in Wentworth in here. This second box, this title box, this is for whatever you call your part in common conversation. It's vaguely descriptive, but you're not, writing a story. So we can call this something like U bracket or 2.5 inch U bracket. This revision number. Think of this revision number like how Apple iterates their iPhones. Apple's been making the iPhone for decades now. It's still an iPhone. However, you've got the iPhone, 5, 6, 7. And what they are is it's the same phone with changes made to it over the years. That's exactly what this revision number is. Anytime we create a drawing, it starts out as revision 1. As you make a change to this, right, you will update this revision. For your drawn by, check by, approved by box, whenever you create a drawing, you're going to put your initials or your name in this drawn by box and the date that you drew it. Once you're done with this drawing, you are going to hand it to a colleague. They're going to check over this drawing and find all the mistakes that you've made in it. No matter how long you've made drawings for, you're always going to make at least one mistake on a drawing. So they're going to check it over, circle all the mistakes, hand it back to you, and you're going to repeat that process. Once they're happy with it, they've got no mistakes in it, they're going to put their name and initials in this box as well. Under the approval box, they're going to hand this to the engineer that designed this part, is going to use this part. They're going to do the same thing. They're going to check it for mistakes, circle them, hand it back to you. Once you fix them all and they're happy with it, they're going to put their name and initials in this box as well. We do this so that we're not sending drawings out with obvious mistakes in them. It's very cheap and very easy to fix a drawing. It's a lot more expensive and a lot more time consuming to fix parts that are manufactured wrong. Over here, this is probably the most important block in this title block. This is where we specify the amount of variation we can accept on each dimension. We can never manufacture anything perfectly, so we have to allow for some amount of variation in each dimension. So this is where we set that. For fractional here, this is where we set the amount of variation we can accept on fractional dimensions. We'll go ahead and put in 1/16. For angular, we have two kinds, machine and bend. This is for machined angles. So if you're cutting a slope on a milling machine, we'll go ahead and put in 1 degree. To get your degree symbol, on your left-hand side, you have this icon. It looks like a CL with a little green plus mark. Let's see. And we can grab degrees. bend is how many or how much variation you can accept on degrees for bent parts. So if you take a piece of sheet metal and bend it, and we'll go with 5 degrees. 2-place decimal is the amount of variation we can accept on dimensions with 2 decimal places. We'll go ahead and specify that as 0.05. And 3-place decimal obviously is for 3 dimensions, or 3 decimal places. And we'll go with 3 thousandths. That looks good. This box right here, interpret geometric tolerancing per. In this box, we are going to put in ASME Y 14.5-2009. And I'll explain this in a second. And we can adjust our font to fit. I think 5-point font fits in there. This is where we specify what standard we're dimensioning to. Now, ASME is the American Society of Mechanical Engineers, and Y 14.5 contains information like how our dimensions are to be interpreted, and stuff like that. So, we usually always dimension to 14.5. Material and for finish. This is where we put what our material is, and as we recall from our model, let's see here. It's being finicky. We made this out of ASTM A36 steel. So our material is going to be ASTM A36. Now finish is for anything you want applied to the surface. Paint, powder coat, anodizing, chrome plating, anything like that. We're going to specify none. This block right here, the applications block. When we make assemblies, what we're going to do is we're going to create a part drawing like we're doing for each individual part, and then we'll create a drawing for the full assembly to show how all the parts fit together. What we would do right here is to put the drawing number for the assembly drawing. That way, if somebody comes across this part and they want to know how it fits together in the full assembly, they can reference that drawing. And this box right here, proprietary and confidentiality. This essentially states that the information in this drawing belongs to so-and-so, and if you steal it, we're going to sue you. This is all garbage and you can delete it. If you're working on anything that requires any sort of legal protection, whether it's patented, copywritten, classified, anything like that, your company's lawyers are going to come up with your own legal verbiage that they require you to paste into all of your drawings. They're not going to rely on that default Solidworks warning label. So it gets deleted on pretty much every drawing I've ever seen. So this looks good. This looks good. So what we can do now is we can go back to our full and complete drawing. To do that, we're going to right-click somewhere on our paper and select Edit Sheet. And here we go. Now at this point, our drawing is complete. So what we can do is we can go ahead and save this drawing. And then what I would like you to do is to save this as a PDF. To do that, you're just going to go to File, Save As, and then PDF. When you send engineering drawings to anyone, you always want to save them as a PDF for a couple reasons. One, not everyone has SolidWorks installed. So if you send them a SolidWorks drawing, they won't be able to open that. Secondly, if you do send someone a SolidWorks drawing file, you also have to send along the accompanying part file. Like I said, because they're linked, if you open up this drawing and you don't have that part file, your drawing will be blank. And sending out part files is not something we want to get in the habit of doing. So always send a PDF file. So if you guys have any questions on this drawing, please feel free to reach out to me. And as always, have a nice day.